Next, we have refrigerant. Very, very important. First, we'll talk about the refrigerant, because refrigerant is a heat carrying medium which we are using in vapor compression cycle. Okay, so first we'll talk about refrigerant, then we can think for vapor compression cycle. In between, I'll play one video. So what we discussed till now, that concept you can find out in an animated way in that video. So so that we can deal with the vapor compression cycle. So what is refrigerant? In short, I can say it's a heat carrying medium during the cycle. Extract heat and reject heat. Extract heat at evaporator and reject heat at condenser. So if you don't know what is evaporator, what is condenser, so you see refrigerants are a substance used in cooling system, air conditioning system, heat pumps, and refrigerator. So air conditioners, it's nothing but a cooling system. But what about heat pump? Heat pump also a same system, but work in a reverse way. Okay, because you see cooling system is extracting the heat from the space and rejecting outside. Suppose if I use in a reverse way, means in winter for Western countries, then we can call as a heat pump. Okay, so heat pump means reject the heat inside the space, and outside it will extract the means reject extracting the heat from outside and rejecting inside. That we can call as a heat pump. So same thing but in a reverse way. And refrigerator. See, refrigerants are used in air conditioners, heat pumps, and refrigerator. Everyone aware of this refrigerator to transfer the heat from one place to other. And this refrigerant is special substance. So about the refrigerant properties and all, you can find in the notes. So you see the desirable properties of refrigerant. The first point you can find on the screen, it's a low boiling point. And this low boiling point is important because with this property, low boiling point means at low temperature it can start boiling, and when the refrigerant start boiling means it can extract the heat. And you see heat absorption property also required, heat rejection property also required, and the cyclic process means the same refrigerant can be used continuously in the cycle, and you can achieve with the standard refrigerant. And what are those standard refrigerant you'll find in the next page. But before this, if we talk about the classification of refrigerant, so all this refrigerant is classified into three categories. One is a CFC, second is a HCFC, and the third is a HFC. CFC is a chlorofluorocarbon, and HCFC is a hydrochlorofluorocarbon, and HFC is a hydrofluorocarbons. So remember, the CFC is almost outdated because the CFC will affect to the ozone layer, the environment, and that's the reason officially it's not used in the market in almost all the countries. They may some people that are using unofficially or illegally, that is a different case, but officially, as per my information, no manufacturing company, means air condition companies or refrigeration companies, they are not using the CFC. But still in the market you can find this HFC. HFC also affect to the ozone. It's also not completely environmental friendly, but compared to CFC is less. Approximately we can say 8 to 10% effect to the environment compared with the CFC. So still in market, you can find this HFC, and the best example of HFC is a R22. R22 still in market, you'll find in the refrigerator, you'll find in the window AC, in split AC, in the water coolers, etc. But now see, for big systems, you'll find HFC, hydrofluorocarbons. So this you see have environmental friendly, means there is no effect to the ozone, but we have some disadvantage also compared with the HFC and CFC. We'll discuss in the next page. So remember, in market you'll find this HFC, and the best example for HFC which is commonly used in the market is R134A. If you check to any four-wheeler air conditioning system, you'll find R134A. Or even for this air conditioning system which is used for commercial and residential, in that also you'll find R134A. Even in chillers also you'll find R134A. Apart from R134A, we have this R410A. This also used commonly as a HFC category refrigerant. And you see, apart from this, you'll find the ammonia also. But again, ammonia cannot be used. Ammonia, you see, in one side, it's a very best, or I can say excellent property for the to use as a refrigerant. But the problem with the ammonia is what? It's a toxic. So that's the reason this ammonia cannot be used in commercial or residential systems. You may find in industrial system where there conditions, but commonly will not use because of this toxic in nature. So finally, the conclusion is for the refrigerant, for interview point of view, You see, R22, HCFC, R134A, HFC, R410A, again this also HFC. Okay, and some properties also have given in the next page in the form of a table. We ask in interview. So go through once related to especially for this 3 refrigerant. Okay, I have given this GWP and ODP different condition. Just go through once, may ask in interview. Actually, this details is required for the service side because in service side you must know the pressure rating and all conditions for the different refrigerants. But for design point of view or for installation point of view, that much of detail is not required. So that's the reason I have given only for the 3 refrigerant. Later at the time of chapter 5, classification of machine, we'll discuss the pressure, the suction pressure and the discharge pressure, the standard for the different systems. But this level, what I've given is just a general information related to only the 3 refrigerant, which can be asked in interview and important for HVAC engineer.
So one thing,
yes,
selection of refrigerant is a part of HVAC engineering,
no,
is a responsibility.
No, it's not a part of a HVAC design engineer. If you are working in the manufacturing side, yes, and that we consider as a component designing. No? So we are not bothered. We are as a HVAC design engineer, we are not supposed to decide this refrigerant, and we are not supposed to even design this copper coil which is inside the systems. We are going to select.
The
No,
VRF system.
no, I'm not about VRF. VRF pipe sizing is a responsibility of a HVAC design engineer.
And refrigerant?
A refrigerant, no, that will take care by the vendor. And you see, apart from this, even if you talk about the VRF, in actual practice, many vendors, special vendors, or the manufacturer, they're taking care of this, even the pipe sizing. But again, as a HVAC engineer, you should know the pipe sizing of VRF. But the pipe sizing of window, split, this ductable different system, that is not a responsibility of a HVAC design engineer. That is a responsibility of the manufacturer. Okay, but in VRF, we are taking a part, not completely, but partly. Even if you're not designing the VRF pipe, you must know this because you are responsible to verify all this on site, even for testing and commissioning also. Again, the testing and commissioning also are done by the manufacturer with their own software. Okay, because that is somewhat precision system. Now, if you talk about chill water system designing the piping, that is the responsibility of a HVAC design engineer.
That is water side.
Yes, water side. That piping is your responsibility as a HVAC design engineer. But the designing of this pipe, except this VRF for other system, I'm talking about the copper pipe, that is not belongs to the HVAC design engineer. That belongs to HVAC. If you're working in the manufacturing side as an application engineer, you are going to involve in that. Okay. So now with this information, we are ready to deal with the vapor compression cycle, which is a base for the different air conditioning systems. That is I can relate this with the chapter 5. Okay, but before this, let me quickly play one video which will help to confirm what we discussed till now, like sensible latent, and in that you'll find the animated side of this vapor compression cycle also. So before starting the vapor compression cycle, let me play this video. This will help you to confirm the concepts what we learned till now, and some more concept like how this pressure is related to the temperature, and how this boiling point related to the temperature and pressure, which is a key point for learning this vapor compression cycle. So let me play this, then we'll discuss about this vapor compression cycle. So I'm going to share the screen with the video mode.
The primary purpose of refrigeration is to eliminate the warm conditions under which destructive bacteria prosper and multiply, and by subjecting the bacteria to conditions of cold to reduce their rate of activity and growth. The process of producing cold is the process of removing heat. Of the 3 effects of heat, refrigeration is chiefly concerned with 2. The first effect, that of sensible heat, is one that causes a change in temperature as read in degrees on a thermometer. In this example, as heat is applied, the temperature of the water in the kettle rises up to 212 degrees Fahrenheit at sea level. At this point, the temperature remains constant, and the second effect, latent heat, is observed. The water changes state and becomes a vapor. Change of state may proceed in either of two directions. When a sufficient quantity of heat is absorbed by a solid, it passes into the liquid state. Upon absorbing more heat, the liquid evaporates and changes to a gas. When sufficient heat is withdrawn or released from the substance in its gaseous state, the gas condenses or changes back to a liquid. When more heat is withdrawn, the liquid freezes or returns to the solid state. For any substance, there are two distinct quantities of heat involved in changes of state. The first, latent heat of fusion, is the quantity of heat that must be absorbed by the substance in the solid state in order for it to change to a liquid. Or that must be removed from the liquid if it is to return to the solid state. The other quantity of heat, latent heat of vaporization, is that which must be absorbed by the substance in the liquid state in order for it to change to a gas, or that must be removed from the gas if it is to return to the liquid state. In mechanical refrigeration, it is the movement between liquid and gaseous states that is important. Absorption or release of latent heat does not alter the temperature of a substance while it is changing state. In this example, although the block of ice absorbs a certain quantity of heat as it melts, its temperature during melting remains constant at 32 degrees Fahrenheit throughout the change of state. Heat quantity is measured in British thermal units, or BTUs. A British thermal unit represents the quantity of heat required to raise the temperature of a pound of water 1 degree Fahrenheit. We know that when a liquid is heated to a certain temperature, it boils and changes to a gas. However, it is possible to cause the same liquid to boil at a lower temperature. This is done by controlling the pressure upon the liquid.
You see, this point is very, very important. So everyone aware of this, the boiling point of water is what? Is online?
100 degrees.
Degrees centigrade.
112.
So now the question is, can we boil water at 10 degrees centigrade? First of all, it is possible or not?
Possible.
So how it is
Possible depending upon the pressure.
Yes, so you see.
Pressure.
So remember this is possible, correct? Your answer is correct. So first of all, you see this 100 degrees centigrade is a boiling temperature of water based on what pressure?
Atmospheric pressure.
Very good. Based on the atmospheric pressure. So at atmospheric pressure, we have this 100 degrees centigrade. So with some ways, if you reduce the pressure, so it is possible to reduce the boiling temperature also. Okay, so by in a closed shell, if you reduce the pressure, so what will happen? Even we can boil water at 5 degrees centigrade with a very low temperature, the water start boiling by reducing the pressure. And remember this point we'll use in vapor compression cycle, because in vapor compression cycle, we are reducing the pressure to so low. So what will happen? The refrigerants start boiling. And when the refrigerants start boiling, what will happen? It will extract the heat. And extracting the heat means producing the cooling effect. Okay, so we will discuss this point, but at this level, just remember, it is possible to reduce the boiling point by reducing boiling point of a substance or a fluid, for example, by reducing its pressure. So just remember this point. Now, let me continue.
The higher the pressure, the higher the boiling point temperature. The lower the pressure, the lower the boiling point temperature. It is through control of pressure that refrigerator temperatures are controlled. We know that heat will flow from the warmer to the cooler of two adjacent bodies, that the flow will be relatively fast while there is a large difference between the temperatures of the two bodies, and will become slower as this difference becomes smaller until it ceases when the temperatures of the two bodies have become equal. When a liquid changes to a gas, it absorbs heat which flows to it from its warmer surroundings. When these surroundings happen to be food in a refrigerator box, heat is withdrawn from it. That is, it is cooled or refrigerated. This is the rock-bottom basis of modern refrigeration. There are three methods by which transfer of heat from one place or body to another is accomplished. The first is conduction. When a flame is applied to one end of a metal bar, heat spreads through the metal, passing from molecule to molecule toward the cool end of the bar until the entire bar is hot. In the process known as convection, heat is carried along by the motion of a stream of gas or liquid whose function is similar to that of a conveyor belt. In conduction and convection, heat is transferred through or by matter. The process of radiation involves the direct transfer of heat in the form of waves, without need for a medium for the heat to move through. Refrigeration makes use of all three methods of heat transfer in removing heat from food items to a liquid cooling agent. Heat travels between the food and the cooling unit wall, both by means of radiation through direct waves and by means of convection through air circulation. The heat passes through the cooling unit wall to the liquid by conduction. The substance which soaks up heat during evaporation to create coolness is called a refrigerant. Its function is to remove heat from one place, leaving that place cool, and to discard this heat elsewhere while it is being changed back to a liquid. To produce refrigeration, all that is necessary is a refrigerant that functions in terms of the physical facts and processes already described. Refrigeration would be adequately achieved if we placed a liquid refrigerant in a box and provided an outlet for its escape following its change to a gas. However, at this point, several practical problems must be solved. To minimize the amount of outside heat that enters the refrigerated storage space, the walls of the box are filled with insulating material which does not absorb heat readily and is a poor heat conductor. A second practical consideration is the cost of the refrigerant. For economy, the refrigerant must be saved, stored, and returned as a liquid to be used again. And this process must be made automatic. This is the purpose behind all the electrical and mechanical devices which we identify with modern refrigerating systems. There are two principal refrigerating systems, the compression system and the absorption system. The basic difference between them lies in the source of the energy that drives them. The compression system operates on mechanical energy produced by a motor-driven compressor. The absorption system uses heat energy supplied by a flame or some other source of heat. The compression system, activated by a compressor, will be described first. It is divided into the high and low pressure side.
Just have a look for this cycle. After this video clip, we'll discuss in detail about all these components.
The high pressure side is that portion of the system through which the refrigerant travels under high pressure. This side starts at the discharge valve of the compressor and includes a condenser, the receiver or storage tank, and the liquid line. The low pressure side is that part of the system through which the refrigerant moves under low pressure. This side starts at the expansion valve, which divides the high and low pressure sides and includes the cooling unit or evaporator, the suction line, and the suction valve of the compressor. The compressor is essentially a cylinder in which a piston works. This is the course of a refrigerant through a typical compression cycle. The refrigerant, in the form of a gas under low pressure, is drawn from the suction line into the compressor. The gas enters the cylinder through the suction valve as the piston moves on its downward stroke. When the piston moves upward, the pressure and temperature of the gas rise. The gas is compressed and is finally pushed through the discharge valve into the condenser. The refrigerant enters the condenser as a high-pressure gas, and its temperature is higher than that of the air or water cooling the condenser. As heat flows from the gas to the cooling agent, the gas condenses, changes to a high-pressure liquid, and passes into the liquid receiver or storage tank. From the receiver, the high-pressure liquid refrigerant passes through the liquid line on its way to the cooling unit. The high-pressure refrigerant must now be reduced to a low-pressure liquid so that it can evaporate at a low temperature. The refrigerant passes through an expansion valve which divides the high and low pressure sides and controls the flow of refrigerant into the cooling unit. The refrigerant enters the cooling unit under a reduced pressure caused by the suction stroke of the compressor. It evaporates, absorbing heat from food in the refrigerator and providing what we know as refrigeration. The refrigerant, now a low-pressure gas, is drawn through the suction line back to the compressor, completing the cycle. This, then, is the cycle of changes of the refrigerant as it moves continuously through the compression system.
Yeah, so I think you got some idea.